Hello everyone, my name is Yuqi. I'm very glad to present our work, Accelerating Adaptive Optics Computational System using Stochastic Leeuwenberg-Mark Method. I'm from COST, so this is a collaboration with Australia National University. These are the co-authors. I'm a second year PhD student under the supervision of Professor David Keyes. So what's this presentation about? In short, I will present this figure and say we use stochastic SLM method, we call SLM, to reduce the time of atmosphere profile identification to less than 1 second on 8 A100 GPU without losing the adaptive optics system performance. This real-time atmosphere profiling is important for AO system. As you can see in the figure, so we can see the SLM finished this is the optimal Strahov ratio level, the higher the better. So this is the time and the Strahov ratio. We need to get the optimal Strahov ratio as fast as we can. So in this figure you can see the SLM outperform the LM much better. The detail of the figure I will explain later, so we'll first explain this. If you remember the Hubble Space Telescope experience, where they have the hardware issue and they use the software solution to address the issue. Here we are dealing with European extreme large telescope, and we also use software algorithm solution to extend the hardware limit. We will first introduce the atmosphere turbulence. So the incoming plane wavefront is the light before they come inside the Earth. So the Earth's atmosphere is composed of a turbulence eddy. So it can be discretized into several layers. So each layer it contains the turbulence strength, can be described by several parameters such as turbulence strength and the bidimensional wind velocity. A feature of the turbulence eddies is that it changes fast. A typical time frame is that it changes from 2 minutes to 20 minutes. So AO system is designed to compensate such distorted light wave. So you can see so let's first look at the figure 2. This is the simplified waveform sensor. So that when the light can reach here, so the photon arrive the waveform sensors, and they shapes the slopes, and we can calculate the slopes and calculate slopes, and then we can get the covariance matrix of the slopes, as it showed here is called CMM matrix. So luckily we can also get an explicit expression of the covariance of atmosphere model on waveform sensor using their physical location and parameters. So these parameters is the turbulence strength and the bidimensional wind velocity. So as you can see, we can get the explicit analytical expression. We can also get the measurement data. So then we can use a minimization. We can form a minimization problem and solve it to get the parameters. The difficulty of this problem is that first, the function f, so which means the analytical expression is complicated, and it is also non-convex. The CMM matrices, this matrix, is usually very large. For ERT, it can go up to 100K times 100K. And also we mentioned that we need a real-time requirement because we need to all the AO operation should be inside should be fit inside the 2 minute to 20 minutes. So except for the identification problem, AO system also need to record the data, clean data, and and also we generate the command for the other component. So identification problem is only one process. So we need to be as fast as we can. The last difficulty is that usually telescope is set up remote. So the power of it cannot be too large, it cannot use a supercomputer, so it's a limitation. So our SLM, it solves the problem by using a subsampling method. So it randomly selects item inside the CMM matrix to form the gradient and the approximate Hessian matrix. Okay, so let's further see the problem definition. So this one is the fx. We think it's a difference vector. So you can see it's element-wise the difference of the analytical CMM matrix and the numerical CMM matrices. So the vector length is very large. So as we said before, 100k times 100k is 10 billion for ERT. So this one is the 10-layer analytical atmosphere model. So we choose 10 layers because usually the EES, so European Southern Observatory, also recommended such analytical atmosphere model. And the numerical, how we get the numerical data, so we need to be collected cumulatively around 30 seconds to 1 minute to get high enough signal noise ratio. After get the difference vector, then we can minimize, we can write down our minimization problem like this one. And we further to have some notation. So this lowercase f is the minimization problem, capital F is a difference vector, and the Jacobian is a stochastic Jacobian. So it selected the item inside the f and to shape the Jacobian matrix. So the gradient is the g, tilde g is the gradient vector, also the stochastic gradient vector of the function minimization function f. Then we describe our axiom. So here we first choose a constant mu, so because we are using fixed regularizer, and we generate a random index sequence random before. So it is, so we find that these random numbers it may lower the performance of the SLM. So we pre-generate, so we generate the random sequence before the iteration process. So the calculation of the approximation, the Jacobian transpose Jacobian, and the gradient is the most time-consuming part. So we deploy the computation onto GPU. Then the criteria, we choose the normalized gradient, which is the gradient at the tilde gradient at the g and divided by the tilde at 0 iteration. And we solve the linear system. So here you can see the left-hand side matrix is 30 by 30. So so this time is very small. So this linear system, we can solve it very fast. So we just use the vendor library. This is the main iteration. Okay. Then we will introduce our theory result. So we have 3 assumptions. We think that the function is error smooth, and we bounded the stochastic gradient, and we also bounded the Jacobian, stochastic Jacobian. Okay, and then this is the theory. So we can see that the average of the gradient norm square over k plus 1 iteration is bounded by a 1 over square root of k plus 1 times a constant. So the color is that we can get the minimum of the gradient norm square over k plus 1 iteration is decreasing over 1 over square root of k plus 1. So this is a classical complexity bound known for SGD invariant. Okay, so I will further explain the new stochastic HG kernel design. As you know that the J transpose J and the tilde G is the most time-consuming part, so we designed the stochastic HG to compute the approximation and the gradient. So each CUDA thread is responsible for 1 sample in the minimization problem, and we get numerical Jacobian using finite difference approximation. The block random index, these are then we will explain the technique we use to optimize the kernel. So if we select index 1 by 1 randomly, we will have memory access issue since we have irregular memory access pattern. So what we do is that we group index together and select the index by group to make sure we have coalesced the memory access pattern, as is shown in this figure. So ID is original item, and we group them so that when we access the data, so we can have coalesced memory access. Another technique is reduction optimization. So in HG kernel, we have 1000 reduction operation. To balance the performance and the portability of the software, we use cube library to perform first block level reduction, and then we use atomic operation for global reduction. Okay, we will show the kernel performance. So as shown in this figure, so this is the performance decomposition over different technique. When we use block random index, we have a 3.6 acceleration. When we further use block reduction, we have seen a 1.27 acceleration. This result is generated on A100. Okay, so then we show strong scaling of HG, and you can see we tested on the 3 NVIDIA DGX system, which each one equipped with 8 GPU. So this is the choice of the power limitation, because we don't have a supercomputer there. Okay, you can see the time for different architecture. When the architecture is newer, so the time will be shorter. Okay, so this is for the speed up result, and we show 3 data fraction, and as you can see, when the data fraction is become larger, so we are more close to the ideal speed up. This is because that GPU has more work to do, so you can get more ideal speed up. And the weak scaling result. So this is the weak scaling result. The same as you can see, we can have a decent scaling result. Further, we show SLM time breakdown and scalability. So this graph shows the time breakdown of one iteration of SLM. So as we said before, we have 2 items here. So first, the stochastic HG kernel and the multiple GPU reduction. So as we said before, the linear system solver and the parameter update are very so they are short in time, so we neglect them. So what is this multiple GPU reduction? So when you finish the HG kernel, so you have to copy the data back to the CPU, and you further do the reduction on the CPU. So we call this step multiple GPU reduction. And we also show the 3 data fraction and 3 architecture. As you can see, when the data fraction is large, or when the multiple GPU reduction can be neglected. It's very small compared to the large stochastic HG kernel. But when the data fraction is low, and when we have newest architecture A100, you can see that these little guys gradually show up. Okay, so let's look at the speed up SLM. So yeah, we also get a good speed up when the data fraction is large. So it's relatively the same, almost the same as the Hessian gradient speed up. Next, we will introduce the end-to-end simulation of SLMs with different data fraction. So why we want to research it? Because we want to find a good data fraction that balance the performance of the AO system, as well as we have a good computational efficiency. So we use the criteria called Strehol ratio. The Strehol ratio is one of the most important criteria for AO system, and we use the true parameters to first test the best performance we can get. So on the AO system, so we get around 25. So as you can see, when the data fraction is lower, so we gradually have poor Strehol ratio. So we are interested in this when the data fraction is equals to 0.001. So that it give us a good Strehol ratio as well as the computing efficiency. Okay, then we show the numerical result using 1A100. So this is the theory and the practical practical result. So the theory is as we showed in the theory page, so it's 1 over square root of k plus 1. And this is the SLM with data fraction equals to 0.001. And then we compare the SLM with LM also with first order stochastic method. So we compared with the SGD, momentum SGD, and the add-on. Okay, so with linear rate we choose 0.5, and this is mu and epsilon. We also set a maximum time out for the stochastic algorithms. It's 10 seconds. So the result is that you can see SLM drops fastest among all algorithms, and LM takes a long time to converge. we also show the difference. We also show the Strahov ratio of different data fraction of different algorithms. So the LM can also reach the optimal Strahov ratio, but SGD and MSGD cannot finish in cannot reach optimal Strahov ratio in 10 seconds. However, we see that Adam can also reach optimal Strahov ratio. Okay. Then let's check this figure again. So we know that the Strahov ratio is the performance of the L system, and we also know that DF is data fraction. So this we are using 8 A100 GPU here, and you can see SLM method with different data fraction reach optimal plateau within 1 second. I would like to check this one. Also, LM, but on the other hand, LM takes around 10 seconds to finish, and this is iteration plot with Strahov ratio, and you can see SLM also converge faster, according to iteration. We only show climbing period instead of the whole SR plot because we just want to research how fast they can reach the optimal SR plateau. And these are the DF. So the DF equals to 0.1 and 0.01. 0.01 takes 0.6 or 1.8 and 0.2 second. We also noticed that LTM also converge fast in this problem, but if we look at the gradient norm plot, it's a bit slower than SLM. And also in operational setting, we can't do end-to-end simulation since it's too time consuming. Okay, we come to the conclusion. So in this presentation, we present the theory for the SLM with fixed regularization, and we also use new stochastic kernel to compute. And we compare the performance of SLM with other first-order method and original LM method. Finally, we shorten the atmosphere identification process to less than 1 second. Thank you, and yeah, I would like to answer the question.